Hi, welcome back. So today we will start talking about a new type of algorithm, which is called greedy algorithms. And this particular type of algorithms or family of algorithms are suitable for optimization problems. Okay, and these type of problems usually go through a sequence of operations or sequence of steps, and at each step, there are a set of choices to make. Okay, so the algorithm usually try to have a maximized or optimized outcome based on this sequence of operations. Okay, and one of the characteristics of greedy algorithm is that uh, it makes the choice that looks best at the moment for now. Okay, it doesn't know what the global optimal solution is, but it makes a locally optimal choice in the hope that it will lead to a globally optimal solution. So it's more of a compromised solution because um, we often don't have access to all the information needed or global information needed in order to solve the problem um, in a guarantee to excuse me, to get the guaranteed global optimal solution. But instead, we need to step back and to look at what the local optimal solution is, and we simply choose that local optimal solution in the hope to obtain the globally optimal one. Okay, and this type of algorithms has a very close connections to the dynamic programming algorithms that we have been talking about so far. But um, for many of the optimization problems, they can be solved by a dynamic programming algorithm. But sometimes using dynamic programming is an overkill. It's unnecessary to solve all the sub problems. Okay, so compared with DP, greedy algorithm usually saves more time, saves more energy, and also leads to the global solutions, the optimal solutions. So in this lecture, we will have three topics. We'll in this lecture, in this video, we'll talk about this particular type of question, which is called activity selection problem. And this is a very typical problem that can be solved by a greedy algorithm. And then we will talk about Huffman codes and the general connection from greedy algorithms to dynamic programming within the next video lecture. So the activity selection problem is to schedule several competing activities that require exclusive use of a common resource. So, for example, a room, and the goal is to select the maximum number of activities that are mutually compatible. Okay, so for example, given this table of all possible activities to be scheduled, not all of them are compatible with each other. So look at for example, the activity 1. It starts from 1 o'clock and finishes at 4 o'clock. Say it's Alice's party. So it is not compatible with the second activity, activity 2, which starts from 3 o'clock, and by the time it starts, the A1, Alice's party, is not ended yet. Okay, so these two activities, A1 and A2, they cannot be selected or scheduled at the same time. Okay, so because we are scheduling the activities for one room, for a hall, and we cannot let A1 and A2 happen at the same place, at the same hall, at the same time. Okay. So we are given this information. So to solve this problem, we are given this information from A1 to AN, and in this case, we have 11 activities possible. And our goal is to select a limited number of activities that can happen in the same place. Okay, and we wish to use one lecture hall that can only serve one activity at a time. Okay, but the goal is to select the maximum number of activities because we want to make the most of the use for the lecture hall. Okay, and in this table we have the starting time and the finishing time for each activities available. Okay, and one more condition we provide is that we also sort all the activities in increasing order of the finishing time. So if you look at the third row in the table, it's the finishing time for each activities. It's already sorted. A1 ends at 4, A2 ends at 5, and A3 ends at 6, and A11 ends at 16, which you can think of it as 4 p.m. Okay, so that's the setup of the activity selection problem. One important notation or concept is the so-called compatible activities. So we can use some notations to formalize this concept. So what are the compatible activities? How do we know that two activities are compatible with each other? Okay, so if given this table, we know that when some activity AI is selected, it takes place during the time interval from SI to FI. And SI indicates the start time, FI is the finish time. So we use square brackets on the left as an inclusive brackets, and these round brackets on the right to indicate an exclusive brackets. So we can use this mathematical notation to say that activity I takes this segment on the time axis. Okay, so we say that two activities AI and AJ are compatible if their intervals, say this is the interval for AI from SI to FI, and the interval from AJ from SJ to FJ do not overlap. Okay, so if after we put these two intervals onto the same axis, if these two segments do not overlap, then we say the two activities are compatible. This is quite straightforward notation that makes sense, right? So, for example, in our case, in our example here, A1 starts from 1 and ends at 4, and A3 start at 3 and ends at 5. So if we put these two intervals onto the same axis, they certainly overlap from 3 to 4. Right? So that's why we say A1 and A2 they are not compatible. Therefore, they cannot be scheduled at the same time. Okay? So if we look at A1 and A4, and A4, according to the table, it starts at 5, right? Which is already after A1 finishes. So these two intervals, they do not overlap. Then we say they are compatible. Okay? And more generally speaking, if two activities, AI and AJ, are compatible, then we say either case should satisfy. So either Si is greater than Fj. So that means the starting time of activity AI is later than the finish time of activity Aj. Okay? Or the other case is satisfied. Sj is greater than Fi, which means the opposite way, the other way. The activity Aj, it starts after the activity AI finishes. Okay, so that's the more general definition of what a compatible activity, compatible activities are defined. Okay, so now let's talk about the largest subset of compatible activities, which is the goal of the activities selection problem. Okay, so given one lecture hall, right, we want to select as many activity as possible. So there are multiple. So if we don't place the constraints of maximum number of activities, we can just arbitrarily choose multiple activities as long as they are compatible, right? So for example, in the table here, A3 and A9 and A11, they can be scheduled at the same time, right? Because A3 doesn't overlap with A9, and A9 doesn't overlap with A11. Okay, but even though they are compatible, but they cannot be, they are not the largest subset. Okay, because we know that we can select A1, A4, A8, and A11. And there are 4 activities scheduled, but they are also compatible with each other. And another example is A2, A4, A9, A11. Okay, so these two cases make more use of their own. Okay, so the solution, ultimately, the solution is to the problem is how to get the optimal solution. How do we get these solutions of 4 activities instead of the 3 activities or less? Okay, so that is what we want to solve within this activity selection problem. Now we can use this visualization technique to help us solve the problem of activity selection. So we can first draw this time axis, and we lay out all the activities upon this figure by the increasing order of the finish time for each activity. So we put A1 first here because it ends at 4, so we draw a little thin rectangle from A1 to A4 here, and A2 ends at 5, so that's where A2 lies. And next comes A3, which is from A0 to which is from 0 o'clock to 6 o'clock, and so on. So we did this for all the activities. Okay, so after we have all the activities, now we can think about some questions, like which activity to choose first. And actually, the activity that we choose first will determine what the next activities that we can choose or that are available to choose. Okay, so and choosing one activity will decide how much time that is left for us to choose. Okay. For example, if we choose A1 as our first activity, then after A1 is selected, then because the time period from 1 to 4 is already occupied, then we cannot select any activities that are incompatible with A1. Okay, so in theory, we can say that there are 16 minus 4 hours left that are available for other activities, right? Because A1 ends at 4. We can only select activities within 4 o'clock to 16 o'clock after A1 is selected, right? So we can highlight all the available resource, all the available time after A1 is selected in this color. And what if we select A2 as our first activity? Then there are only 16 minus 5, which is 11 hours left. And that's the available time for select the rest of the activities. Right? What if we select A3? Then the time we've got left is from 6 o'clock to 16 o'clock. Okay. So one of the idea now we can have from observing the consequences of selecting activities on the available time to the rest of the activities is that we can we should select activity that leaves the resources available for as many activities as possible, right? Because from the previous 3 examples, we see that after A1 is selected, there are 12 hours left. And after A2 is selected, we have 11 hours left. And after A3, we have 10 hours left. So intuitively speaking, which one is the best? Right? It's a simple question. So we want the solution. We want the selection that leaves us as many hours as possible, because we want to select more activities. Right? So this gives us a heuristic to make a greedy choice at each step to select an activity. Okay, and this greedy choice is simply to choose the activity that has the earliest finish time. Okay, so when we make the first choice, if we compare A1, A2, and A3, A1 has the earliest finish time. It finishes at 4 o'clock, which is earlier than 5 and 6. And in fact, A1 is an activity among all the activities that has the earliest finish time. So that's why we choose A1 as our first activity. Okay, after A1 is selected, now let's observe this figure, observe this time axis again. So after A1 is selected, we have the rest of the hours, which is from 4 to 16, available, right? We should select the next activity between 4 o'clock and 16 o'clock. Okay, but not all the activities left are compatible with A1. You see, I highlighted the incompatible activities with red color because A1 is incompatible with A2. They have overlap. And A3 also overlap with A1. And so for A5 and A10, they all have overlap with A1. Okay, so how do you see they are overlap? You just need to compare. You just need to look at the starting time of A2, right? Starting time is 3 o'clock, which is before the ending time, the finish time of A1, right? So as long as an activity, the start time of the activity is earlier than the finish time of A1, then we can say that it's compatible with A1. So anyway, the highlighted activities are crossed out. They're removed from our list. We cannot choose from them because we already choose A1. Okay, so among the compatible activities, what's left? The non-highlighted ones. What is our selection? Well, we need to stick to our heuristic, our greedy heuristic, right? We want to choose the activity that has the earliest finish time among all the compatible activities. And we can find that A4 has the earliest finish time. It finishes at 7 o'clock, which is earlier than 6, A7, A9, and A9, A8, A9, and A11. So that's why we need to choose A4 in this case. Okay. So after choosing A4, we need to do the same thing. We need to first look at which activities are available for being chosen for the next one. Okay, we find that A6 and A7, they are incompatible with A4 because they overlap with A4, so we cannot choose them. Therefore, we must choose from A9, A8, A9, and A11. And the policy is that we need to select the one with the earliest finish time, which is A8. Okay, and then we choose A8. And the next question is the same. We want to avoid choosing the incompatible ones, right? So A9 is crossed out, and we need to choose among the compatible activities. And in the last case, we only have A11 to choose from. So we need to choose A11. And that's it. We have a solution which is A1 to A4 to A8 and A11. That's our final solution that gives us a complete list of activities based on our strategy of choosing the activity that has the earliest finishing time. Okay, so that strategy is a greedy strategy. Okay, because we just want to have a activity that gives us the locally best solution, but we don't know whether this is true globally. Well, it turns out that in the case of activity selection problem, this greedy strategy will give us the best solution. Okay, but it is not the only way to solve the problem. We can think of other heuristics in later slides. And first, we can look at how we implement these greedy strategies using pseudocode. Okay, so here is an iterative implementation of the algorithm. Okay, so looking at the pseudocode, this procedure is called greedy activity selector. Okay, and it takes inputs the S and F arrays. So S, as you remember, it records the starting time for all the activities, and F records all the finish time for all the activities. And then we assume that we have n activities to select from. Okay, so we also assume that the input activities, they are already sorted in increasing order of the finish time. Okay, so that's our assumption. And in line 1, we just record the number of activities. Okay, and we store A1 into a set. Okay, into a set called capital A, and this is the set that we will finally return. So this is the result that this is the variable that we will store all of our final schedules, our results. Okay, and A1 is automatically selected because A1 has the earliest finish time, because we already we assume that all the activity are sorted in the increasing order of finish time. And then we will define some variable k. It starts from 1, and this k is the index for the most recent addition to A. Or in other language, we can say, in other words, we can say k is the index for the most recently selected activity, because we just selected activity 1 to A, to the capital A. That's why we let k be 1. So k indicates that A1, k equals 1 indicates that A1 is the first activity we select. Okay, then we will go through, use a for loop to go through activity 2 to activity n. We will go through all the activities, and within the body of the for loop, we use a if condition to check, to find the compatible activities that finish earliest. Okay, so we will compare the starting time of activity I with the finish time of activity K. So K is the most recent activity that has been added, that has been selected. So among the rest of the activities, we want to compare the starting time with the finish time of K. So if the starting time is later than the finish time of K, then we will add the activity I into the final solution A. Okay, and then we will jump to the next activity. We will let k be I, which is the newly selected activity. Okay, and finally A is returned. Okay, so in this code, k is the index of the most recent selected activity, and it is always the maximum finish time for any activity selected in A. Okay, and that's based on the fact that all the activities in S and F, they are already sorted in an increasing order of finishing time. Now let's run this greedy activity selector procedure using our input example. So all the activities, the S and F table are like this, are demonstrated by this figure. Okay, and we, according to the procedure, A, the capital A, all the activities is initialized with activity 1. It is automatically selected, and K starts from 1. Okay, and let's go into the for loop. So I will start from 2. Okay, and if we look at A2, the starting time is earlier than the finish time of A1. Right? So it is earlier, it is not satisfied. The if condition at line 5 is not satisfied for I equals 2. So we will skip I equals 2. And for I equals 3, as 3 is 0, it's also smaller than the finish time of A1. Okay, so A equals 3 is also skipped. And when I equals 4, it is the first time that the starting time is smaller than the finishing time of A1. So A4 is selected. Okay, A4 S4 is greater than the finish time of A1. So A4 is selected. Okay, so A becomes the union of the old previous A and the new A4. So A is the set of A1 and A4, and K is being assigned the new value of the newly selected activity. K equals 4 after A4 is selected. So from the next iteration of the for loop, I will start from 5. Okay, So when I is 5, it is incompatible with A4. And I6 is also incompatible, and for I7 also incompatible. When I equals 8, it satisfies that its starting time of I8 is greater than the finish time of A4. So A will be added to the activity A, to the set A, and K will be assigned A. And after A8 is selected, I will go through A9 and A10. They are all incompatible, and finally when I is 11, it's compatible, so that therefore A1 will be selected. And that's the process of how this procedure runs on our input example. And it's quite straightforward. This procedure describes the way we think about this problem using the greedy search, using the greedy strategy to select the next available activity. So here I would like to mention that we can actually use a different heuristic to implement a greedy algorithm. So previously we have choose the strategy of selecting the activity that has the earliest finishing time, because the idea is that if an activity finishes early, then we will have more time available for the rest of the activities. So we can think of this problem differently. Like, what if we choose the activity that has the latest start time, right? If it starts late, then that means we should have more time before that activity starts, right? So that's just the opposite way of thinking, but it also has the same idea of preserving more resources for the activity that are left, right? So what if we choose to implement the algorithm using this different but similar strategy? We can kind of also solve the problem, right? So what if we choose the activity among this same data, among these same inputs? What if we choose the activity that has the latest starting time? Then A11 will be chosen at first, right? Then we go backwards instead of going forwards. We will go back to see all the activities that are left, which one is compatible with A11, but also has the latest start time. Okay, so it turns out that A9 is a compatible event that has the latest start time. Okay, and after A9 is selected, we can select from A4 because it is compatible with A9 and also has the latest start time. And after A4 is selected, we can select A2. And it seems correct in this situation, right? But we are missing something because these input data, they are sorted by the order of finishing time, right? If we want to use the start time as our heuristic, we need to sort events by the increasing order of the start time instead of finishing time. And we are lucky to get this optimal solution from this data. But if the data they vary a bit, we might have a wrong solution. Okay, so the actual way needs to the correct way needs to be like we first sort all the activities in increasing order of start time, and then we choose we choose the last activity, right? And then we choose the activity with the latest start time among the compatible activities, which will give us basically a bit different solution, but in this way it is guaranteed to be correct. Okay, so that said, the idea is that the input, how your input is organized, should be connected, should be related to the strategy you choose to use, to the heuristics you use for the greedy strategy. Okay. And lastly, let's analyze the running time for the greedy activity selector procedure. So it's quite simple. There's just one for loop in this algorithm, and that's why you can directly think of it as a linear running time bounded by big theta of n. Okay, but this is without considering the time for sorting all the inputs S and F. Right, all the activities, they are sorted by the increasing order of finishing time. So if we use an efficient sorting algorithm to sort all the inputs data, all the input arrays, then in theory it should take us n times logarithm of n. So that's something you should consider if you want to analyze the running time in a comprehensive way. Okay. Okay, so now let's have a quick quiz about the greedy algorithms for activity selection problem. So the question is, given this inputs, okay, given all the activity information here in this plot, so what is the result? What will be the activities that you select if the strategy is to select the compatible activity with the earliest start time? Okay, so this is a different strategy from what we have been talking about. So previously, the example in the slide is the strategy to select the earliest finish time, right? But this time, what if we select the activity with the earliest start time? Please take out a paper and write down the results of selecting the earliest start time, and also put an answer about whether this greedy strategy is correct or not. Okay, and I will open up a submission window on Blackboard today, and you should submit it by the end of today. Okay, so that's a really quick quiz problem. Now let's quickly talk about the connection between greedy algorithm and dynamic programming approaches. So one of the characteristics of dynamic programming algorithm is that the problem should demonstrate some optimal substructure. So which means the solution to the optimal solution, the optimal solution of the original problem consists of the solutions of subproblems. Okay, so that's also this property of optimal substructure is also demonstrated in this activity selection problem. So if we let this notation big S with subscripts S and J to denote the set of activities that starts after activity AI finishes. So this I indicates we are considering all activities after AI finishes. And this subscript J indicates we are considering all activities before AJ starts. So we are considering an interval between activity I and activity J. So let's Sij to denote all the activities between AI and AJ. Okay, and we wish to find the maximum subsets of mutually activities within Sij, and we let the capital A with subscript ij to indicate such a maximum subset of mutually compatible activities in Sij. Okay, so the problem is to solve this, to find the maximum number of mutually compatible activities within Sij. Okay, so let's say if AK, one specific activity, AK, is in the mutually compatible activities, that is to say, a capital Aij. So if AK is in the optimal solution, which is capital A subscript ij, then we are left with two subproblems. Okay, we want to first find a maximum subset within SIK, right? Because K is between I and J, and the K splits the Sij into two parts, which is SIK and SKJ. So we want to solve the problem within SIK and get the solution with AIK. And we also want to solve the problem of SKJ and get the solution of AKJ. Okay? Then the final solutions of AIJ is the union of three parts. First, AIK. Second, the specific event AK, which itself consists of as a set, and the third part is AKJ. Okay, and the number and the size of the set is the size of AIK plus the size of AKJ plus 1. So this is a very typical optimal substructure. Okay, so if we consider this optimal substructure, visualize it within these input figures here. So if the considering the problem is to find the maximum subsets of compatible activities within the range of 0 and 16. Okay, so our problem can be written by this solution of 0 and 16. Okay, so this 0, you can think of it as the I. The 0 you can think of it as the I, and the 16 is our J. So the problem is to solve the range. The original problem is between the range of 0 and 16. So what if if A4 is in our solution? So that's a if. If A4 is within our final solution, then A4 actually divides all the activities into two parts, right? On the right part are all the activities that start after A4 finishes, and on the right are all the activities that finishes before A4 starts. So we want to solve the two parts, right, individually. We need to get the solution from the range between 0 and 5 and the solution between the range and 7 and 16. And then we need to combine the three parts as a solution to our original problem. Okay? So in this case, if we solve between 0 and 5, we will have A1. If we solve between 7 and 16, we will have A8 and A11. Okay? And the final solution will be A1, the union between A4, A1, and the A8 and A11, which is 1, 4, 8, 11. Okay? And that's just one case. So what if, and this turns out to be the optimal solution. Okay? And what if we choose A5 to be the activity in the middle? Then A5 will divide all activity into two parts similarly, right? And we need to solve the two ranges individually from 0 to 3 and from 9 to 16. Okay, solving 0 to 3 will give us nothing because there's no compatible events, and solving between 9 and 16 will give us A11. So the results will become A5 and A11, which is obviously not a optimal solution. Okay, so having shown these two examples here, what I want to say is that this is because the problem demonstrates optimal substructure. If we want to obtain the optimal solution, we need to go through all possible ways of this optimal substructure. We need to solve all possible subproblems, and this is a very typical dynamic programming approach, dynamic programming way of thinking. Okay, so to summarize a bit, the solution, the original solution of between 0 and 16 is the result of choosing the k and solve the left part between 0 and k and solve the right part between k and 16. And we need to choose the k that maximize the combination, right? Not all k's gives us the optimal solution. We want to iterate over all possible k's and solve the final, and get the k that gives us the optimal solution. Okay, so this is a very typical dynamic programming way of thinking. So if you connect this to the original, to the previous lecture, to our either matrix chain subproblem, matrix chain multiplication problem, or the rock cutting problem. Okay, so if we write this into a different notation, so if we abstract the solution notations with the a of ij, then the a of ij is the maximum among these combinations, in which ak is a one activity among the subset of Sij. Okay, and we can further use the 2D array notation to further simplify this optimal substructure. Right? We can use Cij, which is a elements of a 2D array, to indicate this Aij. Right? So it finally becomes a dynamic programming approach. Okay. But I would like to point out that this is an overkill. So in the case of activity selection problem, we don't need to solve all the subproblems in order to get the global optimal solution. Okay, we just need to solve. We just need to use the greedy approach, or the greedy strategy, to choose the locally best one. Okay. And we will go back to the connection between dynamic programming and greedy algorithms later, when we finish up this lecture. Okay, so lastly, let's look at a different way to implement the activity selection, the greedy algorithms for solving the activity selection problem. So this is a recursive recursive algorithm of solving a problem, which is different from the iterative way of solving it. But we'll see how running this algorithm will result in almost the same results, and how the recursive calls selects the next available activity that is that satisfy the greedy strategy is very similar to how an iterative algorithm does. Okay, so this is how the recursive algorithm looks like. It takes, in addition to the S and F parameters, which contains the starting time and the finishing time information, it also takes two integer numbers, k and n, to indicate the range of the problem that this algorithm will solve. Cool. Okay, so the k indicates that the problem, the procedure will solve, will find the maximum subsets of compatible activities after the activity AK finishes and before the activity AN starts. Okay, so it will initialize a integer I as the next activity right after activity K. Okay, and it uses a while loop to increment I. Okay, and the while loop will break if either one of these two conditions breaks. So either one, I exceeds n. Okay, and or the starting time of the activity I is later than the finishing time of activity K. Okay, and if that breaks the while loop, Okay, so the if condition here checks whether I exceeds n or not. If it doesn't exceed n, it means it is this condition, the break of this condition, that terminates the while. So which means activity I should be selected to be the next activity after AK. And after AI is added into the final solution, it will invoke a recursive call to the algorithm itself, to the procedure itself, on a different subproblem that starts from activity I and ends with activity N. Okay, so this here, line 5, is where the recursive call happens. Okay, so in order to solve the original problem that ranges from 0 to n, say if you have n activities to select, you just need to invoke the initial call on 0 and n to solve the entire problem. And there's one more additional input, is that the f of n, or the f of 0 should be 0. So this is a special elements that will be needed, because in the original table f ranges from 1 to n, but here we will need to use the information f of n when we call the function initially. So in the next page we'll see an example of how the algorithm runs on the inputs we have here. Okay. All right, so in order to solve the problem, the original call should be recursive activity selector on 0 and 11. Okay, because we have 11 activities in total. Okay, so the while loop, the I will start from 1. Okay, because initial k is 0, and the while loop will increment I by 1 until either one of these two conditions breaks. Okay, so when the while loop first breaks, the I should be 1. Okay, because the S1 is the smallest value that's smaller than F0. We know that F0 is 0. Okay, because k is initially 0, and we deliberately let F0 to be 0. Okay, so that's how we select A1, and it will, after A1 is selected, according to line 5, we will invoke another call on I equals 1. Okay, so this is a recursive call. So after A1 is selected, we will invoke the recursive call to the function itself on 1, between 1 and 11. So here here 1 is the new k. Okay, and within this call, I will start from 2. Okay, and we will increment I until either one of these condition breaks. So when I breaks, I is 4. When the while loop breaks, I is 4. Okay, so A4 is added to the final solution, and the next recursive call will be between 4 and 11. Okay, and now this time the I will start from 4 plus 1. Okay, and the next one that satisfies is I8, is 8. I equals 8. Okay, and after A is selected, it will be added, and the next call is from 8 to 11. And lastly, after A11 is selected, it will invoke another call, in which case I will start 11 plus 1. Okay, but this time the I is bigger than 11, then the while loop will break. And in the next line of the if condition, it will check whether I is smaller or equal to n, and that if condition breaks. So there will be no more events added, no more activity added. Okay, so that's how a recursive activity recursive way of solving the activity selection problem using the same greedy strategy. Okay, and I think this recursive way is not as easy to understand as the iterative way, but as we run through the examples, they are basically doing the same operations on the same inputs, on the same input data. So that's it for the lecture today, and hope you find this video useful. And remember that there is a quiz that you need to submit. So you need to write down the answers on your paper, on one paper, and then you take a picture of it and upload the picture to the Blackboard system. Okay. So from next lecture on, we'll talk about Huffman code as a second example of greedy algorithm, the applications of greedy algorithms. Bye bye.